Okay, good afternoon. My name is Dobrea Dan-Marius, and I will present to you in this afternoon a presentation that is related with my activity that was taken in the hover game competition. Mainly because there I had countless problems with my drone. I tried to find a solution, and I will present here the obtained results. The idea is I want to make an analysis of different components that are placed on the drone, of analysis of the influence of this component related to the GPS unit and magnetometry unit, and in the end to find some kind of solution to mitigate all of these problems. First word related with the different type of disturbances. Mainly when you analyze the electromagnetic interference, you must take into account the source, the couple, and the receiver. We have mainly two types of sources, artificial one and natural generated. I know that in almost all the cases, the natural generated perturbances are not taken into consideration, and these sources are based on the solar activity and on the lighting. But at least in two cases, there was extended power blackouts related to the coronal mass ejection. And in the first case, 50,000 people were affected, and in the second case, 6 million people do not have access to the electricity, and so on. From the point of view of the artificial electromagnetic interferences, there are a large number of sources. Your phone, your smartphone from your pockets, I don't know, different type of electric heating system, utility power grid, radars, and so on. But here it's interesting to mention some kind of improper design consumer devices. In such a case, due to this kind of devices, all the area related to a port and the surrounding area were impossible to use to get the GPS data due to such a device. Okay, there are several paths that are connected with the interference that get from the source to a receiver. Mainly we have conducted EMI. There we must have some kind of physical path. We can count here power lines, but also we can count here different type of buses. We have coupled EMI, and in this case, the source and the receiver must be in the close proximity, but there are no such kind of physical path. And we have radiated electromagnetic interference, where the source and the receiver are far away. The radiated electromagnetic interference can be narrowband, broadband, in-band, like harmonics generated by telemetry unit, for example, and out of the band. The out of the band perturbation are one of the sources that are not taken really into consideration, but they can generate powerful interferences, mainly to the intermodulation distortion mechanism. IMD occurs when several external out of the band interference sources combine inside your GPS unit due to different kind of nonlinearity that there exists, and in the end you'll get a signal in your band of the GPS unit, and this will perturb the function. You can have something like second order intermodulation, third order intermodulation, fifth order intermodulation, and so on. But mainly third order and fifth order, they are the kind of processes that generate these signals. To give you a short example, here we have a video source and a receiver that work on that specific frequencies. One moment to see. Okay. And at a specific time moment, another video device is powered up, and these video devices work on 25 milliwatts, and you see that there are no interferences because the interval between them is correctly chosen. The second source is powered down, and the third source is powered up. And you will see in the same mode that there are no interferences. But in the situation when both second and the third one are power up in the same time, you will see that several intermodulation perturbations are generated, and you'll see that the quality of the video signal will start to decrease. You can imagine here that you have some kind of out-of-band disturbances that are generated for a local oscillator from your drone. You go to the wireless in the open space, and there you have another source of out-of-band intermodulation. They combine, and in your GPS receiver, you'll get jamming of the receiver band, and you lose the ability to take the data from the GPS network. Okay. For the methodology, I use all the time in all the analyses hover game drones. I take for each analysis 3 sets of data. Each set will take 2 minutes and at least 2 minutes and 30 seconds. And in all the flight time, the flight management unit recorded around 900 parameters. And these parameters were saved on ulog files. After that, I convert this file in another format, and I use this format with MATLAB in order to extract mainly noise and jamming indicator parameters. But in all the analyses that will follow, I use only jamming parameters, mainly because this parameter is correlated with the electromagnetic environment of the related to the GPS unit. This parameter can take value starting with 0, that means no type of interference, is computed inside the GPS unit, and the PX4 documentation recommends that you must have not more than 40 in order to fly without any kind of problems. But from my experience, you can fly with these parameters around 60, 70, maybe 80 without any kind of problems. But when the parameter goes, let's say, up more than 100, you must to take some precautions in order to don't have problems. Okay, the first analysis was done on the RC channel and the telemetry links, mainly because both of them are able to generate in-band and out-of-the-band interference. I analyzed all of these 4 types of links. The first one is one which the hover game drones is delivered. The other 3 ones are long-range links, and I analyze all of them. For the first link, the RC link is connected for a receiver that sends the data from based on S-bus to the PX4 flight management unit that run PX4 autopilot. And the telemetry link is used in order to make a muffling connection between ground station and the drone. It's a classical approach that is used. If we go to the TBS crossfire, here we have some kind of, here we have a long-range communication, bidirectional long-range communication, and one of the main advantages of this kind of link is based on the fact that you can have the possibility to add an additional GPS receiver, power up by an additional battery, and in the case when your drone crashes, let's say the main battery was ejected, you have the possibility to get the crashing point location without any kind of problems. ExpressLRS transmitter is one of the newest open source standard that is widely used mainly in the FPV world. And mainly I use the main channel of the ExpressLRS, and the telemetry channel I use a channel based on 433 megahertz link. The last analyzed system is based on HM30 system that is also a long-range communication system that support an RC link, telemetry link, and also a video channel. In my case, I do not use a video channel. It was disabled, and more of that, Wi-Fi and Bluetooth feature are also disabled. Okay, in all the results that were presented in short time, I shielded all of these generators, all of these units, and the shield is very easy to implement it. I use food aluminum foil that was warped around the receiver unit, telemetry unit, and on the cable. And all of this shielding are used in all of the other analyses that are presented here. Now, you see here the results. You see that the TBS crossfire link is the best one that generates the lower value of the jamming indicator, and the worst situation is based on ExpressLRS link. But ExpressLRS is an open standard. Open standard, the hardware and the software is open standard, and many producers can get and build different type of devices. In my case, I used RC. I used a receiver produced from a Holybro company, I think. I don't remember exactly right now. But it's possible that you buy another kind of devices, and this kind of devices is possible to have better performances and to get lower value of the jamming indicator. If you are asking how that system will behave if I do not use shielding, you see here the results, and you'll see that in the upper table we have the results obtained without any kind of jamming indicator shielding, and in the lower is the table presented in the previous slide where the shielded is used. You see that you get at least 20 units on the jamming indicator less when you use a shield. Of course, you can have better solution, mainly because I saw in the market that have some kind of copper tapes that have superior performances, and in this case, I'm sure that this performance can be improved, but these are the results. Okay. Now I will analyze different kind of onboard computers. The main idea is each onboard computer has its unique electromagnetic, generate unique electromagnetic fields that influence in different modes the drone components. And I analyzed all of these systems. If, for example, the NavQ and the NavQ Plus were used for the hover game competition, I think that the Raspberry Pi system do not need any kind of introduction. And the last two systems are developed by NVIDIA company, and mainly include some kind of some kind of units that are able to process, let's say, some kind of intelligence system like deep learning neural network. And you have there different kind of parameters of these boards. Okay, in all of the recordings, I used this specific operating system that are mainly different kind of Linux distributions on 32 and on 64 bytes. If the system had Bluetooth or Wi-Fi, they are deactivated. If the graphical user interface were deactivated also, in order to have only the contribution that is generated by the system when process data, in our case when the human detection program were used, and this system were all of the systems process the same video file data from the SD card. Okay, the first results that are getting from the DragonBoard was a little bit disappointed, mainly because the jamming indicator has a higher value of 50. And if you see, this board was especially developed for applications that are sensitive to the noise. And they put some kind of shielding from the memory, system on chip, and so on. But even with this shield, you'll see that the parameters, the jamming parameter has a higher value. If we go to the NavQ system, mainly the jamming indicator had a huge value, and this were of 170, and this value is given mainly by the fact that I use a camera and a HDMI converter. When I removed that from the system, I get a lower value, and the result was, let's say, is expected, mainly because the HDMI system is known to generate a lot of perturbances. When you go to the Raspberry Pi system, please be attention that is a strong relation between the operating system and the electromagnetic interference that are generated. One of the consistent results is when the Ubuntu was used, the 60 bits version generate less interference than the 32 version of the same operating system. And if we go to the worst and the best results, another very interesting results you can see here, mainly because when I use the same Raspbian distribution, we get the best EMI results for the Raspberry Pi 4 boards. The value was 27, and when we use the same operating system with the Raspberry Pi 3 version, we get 54. And this is, let's say, an interesting situation. When you go to NVIDIA development boards, you'll see that if we run the same program in CUDA cores, you'll get less perturbances, around value 29, 31. When the case when you run the same program on the ARM core, and the value is similar with the Raspberry Pi 3 development board. The value are around 50. Okay. Mainly because I use Hover Games drone. That drone use GPS unit of M8 type, but the PX4 autopilot support other type of GPS units, and here I group them based on the GPS chip. We have M8, F9, M9, and other types of GPS that are produced by other companies than u-blox. And the main difference between M8 and M9 is given by the fact that M8 chips can acquire data from free constellation, from the 4 supported, and M9 chips can get information for all the 4 constellations supported. If we the F9 chips have the multi-band approach, this is the main differences. And in order to get the same results the same results from the same electromagnetic environments, in this analysis we take the data from both GPS receivers, and more of that in 2 different conditions. In the first one, it was a drone configuration, the main drone configuration without any kind of additional components, only the components required the drone to fly. And in the second one, I put it Raspberry Pi board, mainly because it's a noisiest, is one of the noisiest boards from the one study that was analyzed previously. And you have the result here, and you'll see that mainly in basic, all the cases, M9 and F9 outperform the M8 chip. And what this will tell you, if you have the previous results of the telemetry channels or the development board, and you use another type of GPS receivers, the results will be better, mainly because, for example, in M9 case, you'll get the information from the large number of satellites, you'll see in the last column there. And in this mode, you can get the information from that satellite that has a better signal quality. And in the case of F9 system, mainly because you have an additional band, in the case when the L1 band is jammed, you can get the same information from L2 and L5 bands. Okay, right now I'll present some kind of methods to alleviate this kind of problems. The well-known solution is to use shieldings, and when you use a shield, that shield is no more or no less than the Faraday cage that constrain your electromagnetic interferences. And if you use frequency higher than 1 megahertz, it's enough for you to use a shield with a thickness of 0.1 millimeter. But a big problem is the gaps or holes that exist in the shields, mainly because, especially when you work with the frequency that are higher than 100 megahertz, the effectiveness of your GPS receiver is paternally correlated with the gaps. And in the same mode, you can shield the cable. You can have different strategy to use shielding. You can shield each component in the part, or you can build some kind of enclosure where you put all your equipment that you want to protect. But here I'll show you another approach where the shield is placed under the GPS, and is some kind of color, wall color between the drone component and your GPS system. And you'll see that by using this kind of shield, the GPS jamming indicators go half. And this proves the efficiency of this system. And more, if you put that shield to the ground, you will get a little bit better results. Okay, a very important thing is to find the best combination of components in order to get the best results. Even if you have a system that generates some kind of disturbances that are lower, this system will be more compatible with another system that generate higher interference in your drone. And from this point of view, you can see that right now, I think you have a better understanding of the situation of all the components, and right now you'll be a little bit more, let's say, able to choose the best combination in order to have no problem in your system. Okay, for the conducted electromagnetic interference, the classical method is to use low-pass filters that are composed from capacitance or inductance. And in this mode, for example, in the left case, that capacitors will ground all the perturbances, and in this mode, your system will be protected. Or you can use an inductor. But here you have, let's say, some problems, mainly because it's very hard for you to understand what is the efficiency of this kind of approach related to your GPS system, and mainly related to the GPS indicator. And in order to have some kind of insight of this problem, I use some kind of ferrite cable clip that was put on the wire that connects the power module with the flight management unit. And you'll see that the results are, okay, this inductance will suppress the higher frequency, but the results that are getting on the jamming indicator are, let's say, 3 points. It's not more, but it's one result you can get. Okay, another important parameter is this distance. The main idea is that the interference weakness with the distance. And the most basic solution is to put distance between the power cable and the signal cable, or to put your GPS unit in a higher position. All the recordings that are done up to this point, I use a short mast of 7 centimeters. And you'll see that in the case when I use a long mast with 14 centimeters, we'll get, as it was expected, lower jamming values, but these values are around 15. Okay, another solution is to use short cables, mainly because a cable is an antenna that is able to generate and to receive different type of electromagnetic disturbances. And the solution is to use short cables here. Okay, another another enemy in the electromagnetic interference battlefield is the inductance. When you have higher currents that change the value in short time interval, you'll get higher noise levels. Okay, one solution is to use short cable, but also it's important to you to tightening the connector, to have better soldering in order to decrease the stray inductance. Okay, you also can use, as another solution, twisted pair cables. This approach is very used mainly in the differential system, but even if you do not have such kind of communication, based on this approach, your loop area is reduced and any effect generated by variable magnetic fields are also reduced. And in the case when you use I2C buses that are connected between two systems based on twisted pair cable, you see that there are some kind of recommendation on the official documentation. And another approach is to use single point ground. This is a common mistake, mainly because you can have some kind of daisy chain configuration. For example, if you have a LiDAR light sensor, the most straightforward solution for you is to connect it to power up this from the flight management unit. But doing in this mode, you will get some kind of this kind of problems. And the solution is to use an BAC, battery eliminator circuit, that will power your sensor, and in this mode you'll get a parallel configuration like in right figure, and in this mode all of these problems are mitigated. Okay, in the end, what can I tell to you? The main idea is if you want to develop, if you want to build a drone, certainly you will have problem with the electromagnetic interferences. And if you want to deal with these problems, you must solve it. Of course, there are many solutions. But, for example, from your point of view, it's not important if you work on a system that runs, let's say, Raspbian operating system, or if it runs Ubuntu operating system. The goal is to get the best results. And this goal can be achieved in by many approaches, and I think right now you will have a better view of this problem. Okay, thank you very much.